Well, this is super exciting to be here with Patrick today. Well, my name is Erica Hughberg, and I have been looking forward to this conversation because Patrick is amazing at explaining very complicated things, but in a way that even I understand. So that is super exciting. If you are here live with us, feel free to say hi in the comments. Tell us where you're dialing in from. I'm in the US on the East Coast outside of Atlanta. But yeah, feel free to drop in and say hi in the comments. Tell us where you're joining from. But yeah, Patrick, who are you and where are you in the world and where are you joining from?
Hey, yeah, I'm a machine learning researcher and engineer, and I am calling from Boulder, Colorado.
Very trendy. Boulder, Colorado sounds so trendy. Yeah. And hi, Christopher there. Nice that you're joining us live. Appreciate it. And you have been doing a lot in your career. Like, how did you even get into machine learning or AI? I feel like we've transformed every machine learning engineer into an AI engineer. We like sort of scribbled over and put a new sticker on people.
That has happened quite a bit, yeah. Yeah, I was programming like as a kid, like building websites on the early internets, and then sometime in college, I got really interested in machine learning and kind of started down that path. And yeah, I taught myself mostly off YouTube, and then I got my first job as an engineer, just regular old software engineer. And I worked on, back when big data was a thing, and everyone was talking about big data like they talk about AI today. Yeah, that wasn't nearly that big of a thing, but I kind of worked in that world for a while, and then I got into Kubernetes for a bit after that.
Yeah.
And then, I moved into machine learning thereafter. And I've been doing this I think I've been doing ML for about 6 years now. Super fun. I kind of love every day I get to work on it. I think it's, some of the most interesting problems we have out there today. So.
And do you feel like it's been a journey of, how to call it? Do you feel like it's been hypey the whole time, or has it become hypey, or do you feel like you've been in a nice spot where it's been very practical and solving real business problems?
Yeah, it's funny, when I first started looking at machine learning, back in the early 2010s, it was like very few companies were doing machine learning.
Yeah.
Hardly anyone. It was mostly like research at universities. I didn't have a PhD. The only people who would get into the field pretty much had PhDs at that point in time. Over the 2010s, it got increasingly popular. I think, frameworks like TensorFlow and Torch and PyTorch all did a ton to sort of popularize it and, allow people to create more applications. Before that, you were doing like backprop basically by hand in Python code, and that, eventually got kind of easier for people with libraries like Tiano, but even that was still super hard. Like doing symbolic back propagation yourself in code is no joke. So then TensorFlow came and made things significantly easier. You got Torch, you got PyTorch, and then you had NVIDIA really ramp up on CUDA, and that allowed us to do this stuff a lot faster. And then, slowly you saw this uptake. But it's interesting, in the 2010s, there were literally no one. I mean, there was literally less than 10 people working on AGI in any sort of setting outside of research. Even the people in research who worked on AGI were laughed at, right? It was
what are you imagining?
Yeah, you're working on a problem that's not going to be real for 100 years. Why would you even ever work on it? That was honestly the attitude, right?
Actually, that was real. People really felt like this was so far away that it was just hypothetical science.
Yeah, oh totally. And people were literally mocked for working on AGI. It was
Did you mock them?
No, I wasn't.
No, I'm still kidding.
I was learning machine learning during this time and trying to do basic applications. I was not on the AGI end, but I thought AGI was cool, and I definitely researched it myself quite a bit. But it was it was amazing how people were it's just totally impractical to look at this stuff. And we get the transformer in 2017, and the interesting thing that comes out of that is it can really scale, right? So we kept hitting these kind of scaling boundaries. In the early 2000s, we sort of get deep learning, and we get this through like finding better ways to stabilize neural networks and make them bigger, right?
Yeah.
And neural networks like slowly get bigger and bigger and bigger. And we have, convolutional neural networks and LSTMs at that point. And like, we're slowly like trying to scale these things. And we hit like walls at each point in time. We get, like vanishing gradients. And like, we solve all these with like different regularization techniques and whatnot. But we still hit a wall, and we hit a wall in like 2015, I think, again. And it was kind of a longer wait on this, like, sort of get past this. Luckily, we had like a lot of good applications we could do, like convolutional neural nets, particularly on the deep end. We're getting really, really good at, just starting to detect things in the world. So I think these are like the first companies we really saw that being successful in machine learning were these CV companies, because they could provide real value. Like, hey, like pick out the license plate and like give me the numbers, off that license.
Okay, yeah.
We can start to do like real world applications, sort
like
of
where you had like value.
Like actual value. Like we weren't just like in a company like doing machine learning and producing no value, which happened a lot, by the way. A lot of companies got burned, so not a lot of companies wanted to do it or invest into it because they saw it as just like too risky of an investment over going with like hard-coded SaaS. So most of the money was just going into SaaS and like data engineering and stuff like that, and very little kind of going into machine learning because there just wasn't a lot of business value to extract. But then we get transformers in 2017, right? And the amazing thing we see about those really early is we don't see any scaling limit. They scale past our current deep networks. And, initially in that paper, they're like, we have no idea how big these can possibly get, but, we're hoping to find out. And, Google came out that paper, and they continued to do some stuff in this space, but really OpenAI picked up the transformer series and started, creating GPT. And you have GPT-1. Shortly thereafter in 2018, you have GPT-2, and what I think is 2019. GPT-3, happens in 2020. And the thing to note about those, like these early transformer models, like you would get text completion, but it was just like mostly nonsense. Like you could kind of see where it was going, right? But it'd go off the rails all the time and just start generating like utter nonsense. It was like you can see these tools were going to be valuable, but it was really unclear like how fast they're going to get valuable, right? And so GPT-3, like it's gotten to the point, and there's companies like Jasper that go off of GPT-3 immediately, and it's gotten to the point where like it's starting to produce like plausible outputs. Like you still need to go and like heavily correct them, but like it's starting to be kind of useful. And then OpenAI comes out with the concept of RLHF, right? So RLHF is, basically where you create these chat templates with agents, right? Where you chat back and forth, and then you basically get people to rank the outputs that the model outputs. So you get a bunch of annotators, right? And they just sit there, they chat with the thing.
They just chat.
They just chat, but every time they get a response back, they get like 4 to 8 responses. Right.
Okay.
So those 4 to 8 responses, they then rank.
Yeah.
Right. So they'll like move them up and down and say, hey, this one's better than this one, and this one's better than this one. Right. And then based on that, you can do sort of contrastive learning and all the reinforcement learning algorithms. And so this is known as Instruct GPT. And it was an open model. And this was like, this is the magic that brought the Chat GPT moment. Right.
Like that what actually made it feel like we had this AI
digital
friend that we could talk to.
Exactly.
And it felt really human.
Yeah, and all it was doing was like optimizing GPT-3, right? And so this is one of the things we've learned about RLHF is, it's really just taking like a base model, which if you think about like a really big base model, the thing to understand is intelligence is compression, right? And like that's the best way to describe it is we're going to take all this information, we're going to compress it down into, the smallest space we can compress it into. And so what we're doing with LLMs is we're basically, taking the entire internet, we're finding every connection between everything and compressing that all down, and we're forcing it to share, create these really deep shared latent representations that we don't even really understand very well, like what they are. We just know that they work. There's recent work by Anthropic and the people out of the, mechanistic interpretability community that are, coming up with methods where we can really like look inside these models and start to like kind of understand more about like the formations that are happening. We can chat more about this. It's a deep interest, area of mine, but
because something that I know that you and I spoke about before was that I had this feeling, because I used to work in search, right? So like back in like 20, what could have been 14, right? And I did just like search, not SEO, not like search Google searching, but like
Yeah.
searching data sets, documents, information inside of a system that was known.
Mhm.
And every time I was speaking to someone, it was like, "Oh, search isn't working really well, Erica, because I'm writing in this very much natural language query." And I'm like, well, the problem is that the stuff you're searching for, the information we have has never been tagged with any
Yeah.
keyword, anything that links it. I don't have anything to understand that those things are related to it. I thought I was going to find this, for example, if you, for example, search for information about the president of the United States, but back then, like Obama was the president, I couldn't necessarily link that you would wanting to know about Obama, right?
Yeah.
That
Oh, yeah.
unless I tagged the information correctly and enhanced with metadata and things in the background,
Mhm.
I'd had to do quite a bit of work from an engineering standpoint to make that work. But
Mhm.
now I feel like something did change. Something changed in how I can do, even like with the embeddings, right? That I can put in a vector
Yeah.
database. I feel
Mhm.
like it's much easier now to even just use that to help a simple search be better. Even though I was doing some vector based comparisons back in 2014, 2015, something changed.
Yeah.
And I am often so confused by what happens, right? What really happens when I use, why are these embedding models quite good at understanding or mapping relationships or saying that these things are actually similar, they sit in the same like world, which helps me then associate two pieces of information to each other. I don't, yeah. Why did that work, Patrick? Why did things
Yeah.
start seemingly being easy to do for normal engineers? I call them normal engineers, not machine learning engineers, because I kind of like to put myself in the normal engineering bracket. Uh, we could suddenly get these tools that were made things so much easier. But what happened?
Yeah, I mean it's all generalization at scale, right? So it's, when you train a machine learning model, and this has basically always been true, right? Is that you want to have a bunch of data and there's this sweet spot, right? So if the model is too large, the model will just memorize the data. Too large compared to your data set. The model's just gonna like memorize it, like just I can put this in my parameters and I can like
Yeah.
push it out. But then if you try and generalize it beyond that, it just will utterly fail if you overfed, right? And then you can underfit the model as well, where you have too little data, for the size of the model, right? And so there's this sweet spot in which like you want enough data that when you tell the optimizer within the model, like, hey, you need to be good at this set of things, and that set of things, like in modern models, is like any random sample of stuff off the internet. So the model might be seeing this like batch, which could be like, in modern LLMs is really, really big. Like when GPT is trained, this is like a million example batch. Like if you go to train one of these yourself or fine tune it, it's like 64 or 128, examples that you would see in a single batch. But one of those might be a physics question, one of those might be like a sociology question, one of those might be just like a general chat and like how you help someone, having a hard time.
Yeah.
And you put those all into a batch and you say like, model, you need to be good at all of these things simultaneously.
Yeah.
And the
Okay.
only way the model can do that, if you size it right, is to produce these like deep representations that can be shared across all those things, right? And
Yeah.
so what we're doing is we're compressing all of that knowledge, like this really wide knowledge, and telling the model the only way you're going to succeed at this task is if you form these deep representations that can like go across all these things, right? So like a good example is like, I see, an apple fall off the tree, right? And that happens 100 times, right? Like I can record the 100 times that happened, or I can record gravity. And gravity is this like compact equation, and that's all I need to know now, right?
Yeah.
And so like the model, that's basically what you're forcing the model to do. Like what is like a more simplified representation of all the stuff you're saying, right? Like can I explain all these different actions through some form of physics, or can I explain it through like some core quality that human beings have, and like the model will implicitly learn those things because you forced it to learn those things. So like what you're seeing with search is like, with transformers, we're able to go really large, and transformers are really able to like find the connections between things. They're basically building out huge associative maps of everything that's happening. And then we're taking those maps and we're trying to compress them. Even further. So it's that's what's gotten better, is now the embeddings have just these like super rich amount of information that's like highly generalized across like all human knowledge, right? So when a human goes in and just asks a query, like those deep representations get hit, and we're able to like match really well, on search.
And then we're able to like see somehow mathematically we then get a representation.
We can go that. It's quite
magic maths.
That's best thought of as magic. Optimizers are quite complicated.
And I do think like what Christopher commented, who still uses Stack Overflow, because something that has happened with these like chat type things is that people will gravitate to, that's funny, there was no pun intended to you talking about gravity earlier, but people will start using these chat interfaces to find out information and learn things. So I think, I wonder rather, are we entering a phase of information discovery that is very different from what we have had before, where we, instead of the humans having to learn how to query the information, we have now, through all of that training that you mentioned, that people actually sat and rated answers and humans trained these systems. Have we got to a point where instead of the humans having to learn how to talk to the computer has learned how to understand humans?
Yeah, that's what's happened in a lot of ways, right? Is like, we take these base models where we just compressed all these connections, right? And then the reinforcement learning is really like learning how to navigate all those connections in a way that would be useful to humans. So we just have this like big goop ball. It's a good way of thinking of it. Like it's just this goop of the internet that we've just like gotten as small as we could get that ball to be able to recreate it, right? And then the reinforcement learning comes in and says like, oh, I've got all this goop, like, but the human wants this thing. So like, how do I like navigate through that goop to like get to the thing the human wants?
And then like complicated maths somewhere.
Oh, just unbelievably complicated math. It'll break your brain pretty quick.
So we have some questions from people live here. Maybe we can start with Rick's question here. So embeddings are a mechanism for a highly compressed knowledge generalization at scale. Or how would you think about this, or how would you recommend thinking about it?
Embeddings, most of what we're doing now with embeddings is like contrastive learning. So we're taking, two examples into a deep transformer model, and we're saying these two things are alike and these two things are not alike. And then we're doing, contrastive, which is more or less a reinforcement learning style algorithm. But we're doing contrastive learning, based on that. And when you do that enough times with an optimizer that can learn off of that, you create this dense what's called latent space. And what latent space means is basically like that compressed goop I was talking about. That seems like we have no idea what's in this thing, but like we know the information's there because we can extract it back out. So like we know it's there and we know it's representative. We could not, without like these very recent methods, like we have no way of telling you like what's actually in that space. But doing this contrastive learning at like a really, really big scale. And again, you're doing like million batch sizes to get these really good embedding models. But you're basically saying, like these two things are together, these two things are apart. And so like now you take a given piece of text, you embed it, and you can take another piece of text and you can see how close they are in that latent space.
So basically you're basically just comparing things. Is that what you're saying? Like you literally train it by comparing
things. Those two things similar. Goop, like in a mathematical way, you're comparing those two things of goop because the similar things have gotten, pulled together and the different things have gotten pushed apart. Right. And so this is the same thing that happens with text tokens. So like when you go into an LLM and you say, how are you doing today? Each one of those is broken up into tokens, but those tokens are looked up in an embedding table. So the tokens themselves have their own embeddings, which has happened also with the transformer and contrastive learning. And those embeddings are what actually goes into the LLM model.
Yeah, because it's also so interesting that we can mathematically, I guess that is what it's all about, what you're talking about, is that we can relate in a sentence which tokens and how much they are
Yeah, no, I
affecting
mean,
each other.
and that's really been the biggest, sort of innovation, is just understanding how to build out. It's really representation learning. Like, that's the era we're kind of at, and we're moving to this era of experience. But
Mm,
we're in this era of representation, of really understanding, like, how do we build these latent spaces in a way that they're just super duper rich and
yeah.
super duper compressed. And it's all about, like, how much can we compress down those representations, and like what methods can we use to like compress them
Mm,
further. Because once they're compressed, then it's like fairly easy to take something that we call a decoder, to go
yeah.
off of that latent space and say, like, oh, there's just super rich, super dense information here, and now I'm going to like generate text off of it, or I'm going to generate
Yeah.
images, or whatever else you kind of want to do out of that space.
And we have another audience question here,
Mhm.
which is, at what point do you start implementing guardrails? When do you say that connections, mappings, when do you say what connections and mappings it shouldn't make? I think, by the way, guardrails, I also find that a very interesting conversation,
Totally.
because I have just recently started looking at that. So would love to hear your thoughts, Patrick.
So yeah, so with guardrails, this is all RLHF as well. So it goes through a set of questions, and typically, like, with most of these models now, it's a static data set. So like annotators have previously gone through, they've highlighted,
Yeah.
things that come out of the model that need to be flagged, and then they, try to train that behavior out of the model again with reinforcement learning. It's again just a form
Yeah.
of RLHF, but you're saying, really what you're doing is, when you generate out, say, those 8 responses, you're trying to find all the paths that exist in that model, right? Or
Yeah.
that are highly probable in that model.
Mm,
If you generate out 8 and 2 of them are bad, like, that's a pretty strong signal that, like, you have enough bad probability here that, like, we
yeah.
need to, get that out of there. And so we need to correct that in some form with another set of training examples.
Well, I'm starting to feel like basically at the core of everything, reinforcement learning is the key, because we keep coming back to that in this
Yeah.
conversation. I never really thought about it that way
Mm.
before, that is the key
Yeah.
to what we are experiencing. So if you look at where we are today, and we have all of these tools now that are available to us to build things,
Mm.
what does it actually take to turn all of this goop and somewhat unpredictable maths and what's going on, and turn it into actually like solutions, like AI powered solutions?
Yeah.
Because using a model is one thing, but actually putting it to work,
Yeah.
there's a
Totally.
gap
Totally
there.
different.
And I feel
Yeah.
like we often maybe don't talk about the good model, how to solve problem, and what are your thoughts there? What are you seeing? What's happening? What people building?
Yeah, there's a huge gap there, right? Because everything, in the space of LLMs is probabilistic, and that turns out to be really, really challenging when you get into things that need to be very discrete and symbolic in nature, right? And so
Mm,
we could take code like as an example, and I think this is probably the best use case of LLMs today, is just their ability to generate code, and they've gotten extraordinarily good at this now, like just shockingly good,
yeah.
right? And a lot and that also goes back to reinforcement learning, right? So like in
Mm,
the pre-training and like mid-training phases, we'll have it just ingest a ton of code. We'll basically
mm,
say, like, predict the next token. And this is how
yeah.
pre-training happens. It's like, so like you take a code file, Python or whatever, and you just go token by token, and you tell the model,
Yeah.
generate the next one, generate the next one, generate the next one, and you give it a loss based on that. And so we do
Yeah.
pre-training, on that data, and then it's, reinforcement learning kind of comes after that. And the modern thing on that is what's called RLVR. So it's reinforcement learning verifiable rewards. What that
Okay.
is, like, typically with reinforcement learning, you have some sort of reward model, right? That says, like,
Yeah.
hey, I took this action, and the reward model gives you like points. It's like, oh, you did good, you did bad,
So what
whatever.
people do with children, you
Yeah,
get points.
literally, right? And like the interesting thing about RL is the one instance where, like, machine learning has actually informed neuroscience. So if you look
Yeah.
at temporal deference learning, that was actually taken from machine learning and applied to neuroscience. And they figured out
Oh,
that algorithm is actually what happens in your brain. And so it
like,
was like the first instance of it going backwards. Because you
because I would have thought it would go the other way.
yeah,
I
yeah,
would have
yeah.
thought that neuroscience was informing, but actually we've been able to do it
We've been like, yeah, only
other
a
way
couple of
around.
times, but yeah, that was one of the times where like it actually does, mimic the dopamine system in the brain,
Yeah.
which is super duper interesting. And so yeah, we with DeepSeek that came out, we had OpenAI o1, right, which is this amazing reasoning model,
Mm.
and we didn't really know
I
how it
find the
worked.
whole reasoning thing quite confusing as well, because maybe you can explain that a bit more, because I just feel like it sounds like something that feeds itself, like it eats its own tail. But
Yeah, that's not totally wrong. Yeah. Yeah, so we had O1. O1 was like this amazing model, right? And everyone was like, oh my God, it's scoring like off the charts on all these like science and math questions. Um, and so no one knew how it worked, right? And then DeepSeek comes out and they basically figured out how
Mm,
it worked. And it was this thing called RLVR, which is we're doing reinforcement learning, but instead of a reward model giving you points, it
yeah.
has a deterministic answer, right? So like
Mm,
code or math, like math has one answer you can have, and that's it, right?
yeah.
And why this is important is, in traditional reinforcement learning where you have a reward model, the agents learn to hack that reward model. And there's a
Mm,
couple of like notorious examples of like teaching AI to play video games, and it just learns. I forget, it was like Coast Runners, and it learned
yeah.
like it could just go in a circle endlessly in this one spot and it would like win
Yeah.
the game because it would get
Huh.
all the points, right? And so like it just learns to like do the
Yeah.
easiest math. And so like this happened with RLHF as well. Like it was just learning these like cheats through it, and the model wasn't like
Mm,
truly learning the math or whatnot behind
okay.
it. So with RLVR, we're not having a reward model that can hack, and instead we're like telling it, you have to get this right. This is like a logical thing that you
Yeah.
cannot fake. And then we do this now with like an algorithm like GRPO that was released in DeepSeek, where again we generate out like 8 responses, but then they're each just scored as like right, wrong, right, wrong,
Mm.
right,
So
and
they're
then
not like stacked as better or worse. They're
yeah,
either it's black and white at this
yeah,
point.
and you can't stack them as better or worse than GRPO, but like I think the thing that got us kind of where we are today with coding and whatnot was they're just black and white, and then you average them across that group. So you say
Mm.
like relative to like the worst performing one, how much better was the good one, and
Mm.
that is how you update the model right now. And so it's group relative is kind of
Okay.
what we got there.
I had
But
no idea about this.
yeah. So like RLVR gave us these modern reasoning models, and yeah, reasoning. What you're doing is you're saying I'm going to give you a point for the right answer. You got 2 plus 2 equals 4. I'm going to give you a
Yeah.
point, right? But I'm also going to give you this space where you can
Yeah.
generate out reasoning. And sometimes we do a little like pre-training before this to like explain what reasoning is and maybe how it should look. Sometimes we don't, right? And so like in the case where we don't, we just say like, here's a point. You go and generate it. I'm going to give you the space to do reasoning. I'm going to give you 8,000 tokens or 100,000 tokens,
Yeah.
and you can just start generating, and sure enough it starts like thinking through what would be the right answer if you do that long enough, and it turns out that
Yeah.
works really really well and gives us like more deterministic LLMs, although they are a bit more fragile, is kind of the trade-off you get there.
So do we still believe that there is this need for deterministic AI, like more traditional machine learning,
Yeah.
alongside the generative?
Yeah, I think that's a big question now. I'm like a connectionist to the core. Like I think, we've seen this a lot of times through the history of machine learning of like we need symbolic AI and we need mixed AI. And we have had some success there, like AlphaGo and whatnot is like
Mm.
a mixed symbolic system. And we will probably need that. I think the way LMs do that today is like they just call deterministic tools generally.
Mm.
But we are still sort of missing the like, the LM itself is highly probabilistic. It's interesting to think about like our brains are highly deterministic. They're
Mm.
kind of probabilistic at scale. Like if you get out,
Okay.
there's like enough noise that you can maybe like when they model it at scale, it can, probabilistic algorithms probably going to perform the best. But your actual brain is a
Yeah.
deterministic algorithm. And like every
Oh.
time you send the same input through, you will get the same output because it's like literally just neurons
Yeah.
firing, within like, and there's like interesting stuff that comes with like timing or whatnot, but like neuron turns on or off. There's no
Yeah.
probability to it. It's
Mm.
just like mechanistic, which is quite
Yeah.
interesting. Yeah.
Oh, that's quite interesting. I never thought of our brains as deterministic because they feel, I would say, living with a brain, sometimes it feels that it's not deterministic at all.
You would think it's the
Sometimes,
opposite, right? Yeah,
yeah,
you totally think that. But yeah, they're oddly deterministic. Yeah.
that's quite interesting. We also have another comment question here from Rick, which is, you're saying currently the models are being trained alongside another model that gives it points each time it comes up with the right question to trigger its dopamine reaction for learning better. Then what is your favorite closest similarity between models and human brains? I think we sort of touched on that, but like, is that the parent and the child? The other model training?
Yeah, I mean it's any positive or negative stimulus from the environment, right? So reinforcement learning, at its core is just like you have an agent, and whatever an agent might be, it could be a deterministic program, it could be a machine learning program, and it's operating within an environment. And so it can take actions in that environment, and it can get rewards for the actions it took. And so there's a guy, Richard Sutton, who came up with most of this field. He's super famous. He also has this paper called The Bitter Lesson, which has been like the most influential paper in modern machine learning. But he developed all of reinforcement learning, and it's all has this very mathematical base that is extremely hard to understand if you really get into it. But like,
I probably would not understand.
Yeah, no, I've read the book like 3 times, and I still every time I'm like, wait, what is happening here? But yeah, it's basically like Markov chains, which are a really old idea that came from the early like 1900s. But we've expanded on that over time of like, how do we deal with sequences, right? So like, and this is like sequence. I have a sequence of actions, and I get feedback from the environment at every step. And how do we learn over those action chains? And the hardest part about this is credit assignment. So it's like, hey, I got to like the end, but maybe I took 20 actions and I only needed to take 5, right? And so which of those actions was good and which of those actions was bad? Because often you don't get rewards at every action, you get rewards at the end. And then you need to like figure out like, how can I make this better? And like compress down that action chain. Again, compression, right? So it's
how
like,
to optimize my way. How do I optimize my how I achieve the outcome?
Yeah. And so like modern LLMs, like a lot of it is like, can they set their own rewards? And this is like one of the big things that's being learned right now with continual learning overall, which continual learning is getting super hot this year. It's probably like the hottest topic in AI. And
so what does that mean, really?
Yeah. So continual learning is, how do LLMs just continue to learn from the environment, right? So like right now we have these LLMs, we do these massive trainings, they get locked in time, and you'll see like you can ask them, and they'll be like, my knowledge was cut off, January 2025, and that's all I have to go on. And so they don't continue to learn outside of maybe like context engineering or like memory going into it. So the open question is like, how do we get these things to just continuously learn the way humans do, right? And so one option is you do reinforcement learning, but the LLM sets its own goals. And sort of like, hey, if I achieve this, that's a good thing, and I should sort of learn the outcome of that. So the other ones are like, Google has an algorithm called Titans, where it's like compressing its knowledge across tasks, right? And it just has like a memory module like plugged into the transformer. And it's able to update that memory module sort of as it goes. And this is sort of like combining RNNs with transformers. And that works quite well too.
So if we had this continuous learning and we had a model that does that, so for example, if you use a SaaS provided model from a provider like Anthropic or OpenAI or Grok or any of the other ones, right? And you are using then something that can continuously learn from the world and the environment like a human would, which, I mean, I am still Erica, but I know a lot more than I did even yesterday. Even from this conversation, I have now learned a bunch of things. Would imagine that you are then using a model. So the model you used yesterday can now produce different results tomorrow or today based on what's happened in its environment.
Yep. Yeah. And yeah, sleep gets into this a lot too. So it's like interesting to almost think about it as like you accumulate, humans at least accumulate this knowledge throughout the day. And it's almost like in context knowledge or like short term memory, knowledge. And then when we sleep, a lot of this knowledge gets like deeper learned. And like I almost think about that as like that's like more of the training happening when we sleep because it's learning these patterns and how they blend into its deeper representations. And this is, theoretically like also why we have such weird dreams, right? It's not like it's trying to integrate all these like weird pieces of knowledge into like what's already there and like what's the best way to like compress that knowledge in.
But how will you as a user then like would you not no longer change the model you're using? You just keep using the same one and that one just gets better?
Potentially. Yeah. I don't think we know. Yeah. I mean, hopefully like we all have these highly personalized models that we're able to like teach, to do whatever we want them to do and learn the things we want them to learn and, have them kind of get better at that, in real time. And I think, that's where the industry is going with continual learning. And, I think it's super exciting. It's also a really hard problem. And I heard a researcher out of Google was recently giving a talk and he said, we don't need continual learning for AGI. And I think that gets into maybe the definition of AGI, but I think that's also true is like we could have AGI first and we could get continual learning after that because they're not actually dependent on one another. Like if you consider AGI the ability to learn from the environment, then yes.
Yeah.
If you consider AGI just like the ability to do a bunch of tasks as well as a human, across environments, maybe embodied, maybe not, then no, you don't need continual learning, right?
But something that does continually learn feels way more human because that is what humans do.
Yeah. So there's an interesting question there of like, is that AGI or is that not AGI? But
because I guess there's a fluid definition as well. And I guess it's more about what we want to help us be more productive and do more. And we do have another question here. Can or do different models learn or reinforce from other models? So can you like put them together and they can teach each other stuff? Maybe. I don't know if that was the intention of the question, but that little picture came up in my head. Like you put them in a little classroom and then I start teaching and learning from each other. But
yeah, I think we're seeing more and more of this. I mean, generally, there's been an old paradigm, which is just like teacher-student models, right? And we see this a lot today in distilled models. So generally, like what's trained, out in the ecosystem today are these huge models, right? Like if OpenAI is doing it or Grok or Google, we're talking about like, what's rumored to be like 5 trillion, 10 trillion parameter models, right? Or in the open source, maybe 500 or 300, billion parameter models, these really, really big models. And the reason why that's done is they learn a lot faster on less data and they're able to learn a lot richer representations if you have good data. And then what we do is we take that super big, super smart model that is also really, really slow because it's huge.
Yeah.
And we have it train a smaller model. And this is why you see like on the ecosystem, like 1B, 3B, 7B, those are all distilled from a really big model. And distillation is interesting that, rather you can do it a couple different ways. One is like, you have the model just like output, synthetic training examples, right? Like you should learn this and this, and you can kind of get it to do like a curriculum, right? So it's like easy stuff and hard.
Go to school.
Yeah, I mean, literally, that's kind of what we do, and that works. Like it forms better representations that way. But now what we do with distillation generally is like, when you ask it to predict a token, first it predicts out the full probability space of what the probability is for every token in its vocabulary. Right. So that can be 200,000 tokens of vocabulary, which is pretty common. You're going to get a score of what the likelihood each one of those tokens is to be the right next token. Right. And so what we do now with distillation is we like teach the student model to produce that probability distribution rather than just the next token. And this like dramatically speeds up the ability to do distillation.
That's quite interesting, actually. Well, that was really helpful visualization in my head, at least, when you talked about it as also talking about this huge vocabulary of tokens and then talking about them as we have all of these probabilities of which one of those in our big like universe of tokens, what is the most likely one? And then instead of just saying the answer of one token, you then produce like, well, this is my probability. Is that what you're saying? Like
Yeah, yeah.
basically,
It's kind of funny to think about how it works. It's just like a massive classification problem, right? It's like we used
yeah,
to have like simpler class, you can have multi-class or single class classification of just like, was this good or bad? Hot dog, not hot dog, right off Silicon Valley. Like you just basic classification. And then,
yeah,
with transformers and LLMs, we just like took that to the max and we're like, like you could classify like what token is right, and this is
yeah.
just a multi-class classification problem really of like which one of these is most probable out of like my entire vocabulary of tokens. It's almost funny to
Mm.
think about, but like that's how it works.
Much, very large vocabulary as well. And I guess
Dude,
depending on the model, the tokenization algorithm. How much does tokenization algorithms differ between models, or do you feel like people have settled on?
wildly different. Yeah,
Yeah,
just like almost different for every model, but they
yeah,
are, there are some similar algorithms in there, but like people are constantly innovating on tokenization. And I think, the most modern techniques are like, the byte latent transformer or whatnot, where we're, rather than focusing on text, we're focusing on bytes at that
mm.
level. And that
Oh,
obviously has a lot of advantages because like, the tokenization space right now, think about all the tokens just in English and then think about them across every language on earth.
yeah,
Right. And now you just have this like massive amount of tokens. So yeah, byte latent transformers just try to, compress byte information based on the complexity
mm.
of bytes. So
Yeah,
like if you have a really complex set of bytes, maybe it's like an image or something, it'll give it multiple tokens. And if you have just like white space and text,
mm.
super simple, it'll maybe just give it one token across like a span of a bunch of that white text.
Mm.
So it's sort
It's
of
almost like
compressing bytes.
PNG. It's almost like the PNG image format where we just like repeat
Yeah. So there's
the pixels.
lossless like compression algorithms that are fairly similar. This is learned, so it's a little different than that. But
Yeah.
yeah, I actually met a researcher the other day who had also like implemented lossless compression of like tokens into LLMs, which is quite interesting. Very similar to PNG. Yeah.
Yeah. So you was like, my brain did this weird thing where I was like, wait a minute, this sounds
Yeah.
similar to something else in my
Yeah.
life.
That's totally correct. Yeah.
But what of all of these things are happening in the world of like sort of that I feel like this is a science part of this magic that we are using. And if you are, say you are a general application builder and you want to add AI features into your app, whether that is you want to do amazing recommendations or you want to do maybe you want to do some type of chat-like interface. I'm starting to realize a lot of people tend to gravitate towards the chat-like interfaces, even for simple things.
Yeah.
And maybe that is a natural thing for humans to interact with a computer, because even back when I was doing search, the weird stuff that people would put in the search box as if they thought they were talking to someone is maybe something that humans like doing. And then my question here is, how much of what's new and what's on the horizon do we believe will impact how a software engineer is thinking about the orchestrators they are building around these models and the guardrails or other stuff they're putting up around it? Is things going to change? Or if people are learning those things, is it going to stay the same, but the models are going to get better?
Yeah. I mean, I think the biggest thing changing right now is like we've just hit another level of reliability, and you can see it with the coding agents. Like we've crossed some valley there. I think that's clear with a lot of people who are software engineers, that these models are like getting to the point where they are most of the time right. Which is like across very complex tasks and across longer horizons. And like even the horizons thing is maybe the most important. Like how long can a model operate independently out on its own? So what I encourage, people to think about in general is a couple things, but it's, you now will very soon, and you kind of have today, the ability to do really long range tasks. Right. So like if I'm thinking about an application, like how could I build my application that, in that manner, that now like I can really let the agent go for longer. Right. But how do I still kind of have guardrails on that agent in case it starts to go off the rails, and, having the human in the loop at the same time. And then, with the human in the loop, how can I learn, from course corrections or whatnot? Is a
Mm.
big piece of it as well. So yeah, I think that's where the ecosystem's heading in general. And I don't, with builders, I think the thing that's getting missed the most right now is that there's a lot of people talking that like the models are going to get commoditized and like
Mm.
they'll all just kind of be the same and like it's going to be this dial tone of AI. I think that's like an insane perspective. I think like we're going to have a ton of
Yeah.
models and they're going to be like organisms, like we have a ton of animals and whatnot
Yeah.
on Earth. And like I don't think it's ever going to be like that. Like what's way more likely to happen, and what we're already seeing happen, is that the app space is getting completely commoditized, right? Like within
Mm.
2 years, I would say the app space is going to be gone. And it's going to be replaced with LLMs just dynamically creating applications. So if I
Yeah.
ask an LLM for something, it'll present me with a UI that's like perfect for the task that I'm asking for.
Yeah.
So all the like static front end code will go away and it'll just be replaced with the LLM just generating that as it needs to generate it to give you the best interface to solve your problem.
I think that is a really valuable insight. It's funny because I was thinking a little bit about that yesterday, even.
Yeah.
The reason I was thinking about it, I think some of people here know about the whole ChatGPT Health that
Yeah.
was announced yesterday, and
Super cool. Yeah.
yeah, super cool. And then I was thinking about little things that I do in my healthcare journey. Like sometimes the doctor will be like, "Oh, Erica, can you track these symptoms that you are having? Because I can't help you unless I know how often this happens to you."
Right. Yeah, exactly.
Right? So you need to track it. And then I was thinking, well, what if I could just chat with some things? Say, hey, I need to track how often I have shooting pains in my back.
Yeah.
And what if it could very quickly make me a UI in which I could track that and then have rather than me, or what if I could just chat with it and say, oh, today I had that, and it will know the date, the time I wrote it, and it will track it nicely for me that I had that symptom, but I don't have to go and track it. I don't need a dedicated symptom tracking app. Does that make
Yeah.
sense?
Yeah, which is annoying, right? And like, could it just call me every day and ask?
Yeah.
And that way, like, I don't even have to remember. And like, I just get a call. I'm like, oh yeah, this is how I'm feeling. And, and
Yeah.
that all gets kind of tracked. Yeah. I mean, I'm really excited for the medical stuff in general. We've heard already, amazing things out of the community of people just like figuring out diseases they had that they had no idea they had.
Yeah.
I mean, obviously there's a downside of the models aren't perfect and some people have been misdiagnosed. And, that's, something you should always triple check and you should always ask a doctor, but like be able to really like, just chat with something and like really give it all your symptoms and have it come
Yeah.
up, search across all the literature, give you all the sources and be like, here's, a theorized outcome, I think is, when you think
Yeah.
about how expensive healthcare is and the lack of doctors and nurses and all that, like this is going to be just a huge boon on the ecosystem.
Yeah.
So.
And I think it can help people better express their symptoms to a doctor. Yeah. So they can actually go to the doctor and be like, express themselves better because they've actually talked already about their symptoms. And the funny part about when we talk about things, we actually understand it better ourselves. So actually talking to something that can help us synthesize our thoughts, our things, and maybe even AI can help you present what you are experiencing better to a medical professional. So they don't have to sit and interview you and get to know you over a long period of time to really understand because you are better at expressing it yourself. So,
yeah. And a lot of people are like embarrassed about medical problems or like therapy or whatnot. Like most people like lie to their therapists, right? And there's like this whole end of it where it's like, particularly if you have like a localized AI, like I don't think anyone will lie to that, right? And like so now you have this whole other level of honesty and like maybe encouragement to like, hey, you should like go talk to a doctor about this.
And maybe you should probably mention these things that you mentioned to me.
Yeah,
like, here's a bullet point list of things that would be good if you bring up. And we are running out of time, but you just mentioned localized models. I think that's such an interesting topic as well. Are we going to get there? Like, on a very quick thing, do you believe we will get to, like, will I be able to run a model on my phone or my computer? That's my cute cat. No one can see, it's all blurry. That's my cat. But will we be able to run little models, specialized models maybe, on smaller devices? I don't know if my phone is ready for it, but
Yeah, I mean, we're doing it today, right? But they're not great. Like small models today, you get on anything under a 7B model, and it's pretty rough, right? Like, yeah, you'll get weird outputs, you'll get completely wrong outputs, you'll get utter gibberish, like it gets into like weird loops where it just like outputs the word the 1,000 times or whatever, right? You're like, what is happening? It's like we're not there yet, but like, someone like Karpathy, if you hear him talk about it, he really believes like we'll get down to like million parameter models that can do what like GPT-5 is doing, basically just through tool calling, right? And like they just have this like core intelligence that is like very, very small. And I think we'll eventually get there. I don't share his view on that. I think like just based on the model training and whatnot I've done, I think in order to like really reason across things, I think you just need this model with all these deep connections. And this is the thing small models are bad at, is reasoning, right? Because reasoning requires a lot of parameters. It requires a lot of this like latent space that like Goop I was talking about. It requires enough of that to be like, oh, I can draw these connections across these like disparate areas and come up with the right answer, whereas small models just like don't have the capability to do that.
So it's almost like large models have what humans experience as intuition, where we're just like, oh, I feel this. I feel like this connecting. I can't fully explain it, but I feel it.
Yeah,
and that's what they get.
Yeah, the GPT 3.5 paper, or Instruct GPT, was called, large language models are few-shot learners. And this is kind of the outcome of like, at some point we scaled them large enough that we got emergent behavior, right? Which never happened before. And we didn't think was going to happen for a really long time, actually, at the time, but we saw it almost immediately. Transformers was like, we're seeing it understand how to do things that we never trained it on, right? And it was just like, it was able to combine all these concepts and be like, oh, like, this is actually like how I would do that. And that's, kind of the magic we get today.
I definitely feel so magical. And so lastly, your closing advice to builders who are starting today, that weren't there 10 years ago, not 5 years ago, not maybe a couple of years ago. If you are starting today, what should people be focusing on and learning?
If you're starting today, you just want to build an app. I mean, I think now's a great time to build an app, right? Like the models have just gotten extremely good. You should be able to completely vibe code pretty much any application you want. I mean, I'm vibe coding like whole machine learning, architectures from scratch. Like you can do almost all of it now, vibe coding. So don't be afraid of it. Learn how to do vibe coding better. Learn how to
vibe code yourself to a really smart AI powered app.
Oh,
so
absolutely.
You can have
vibe. Yeah.
Like if you want to build your own orchestrator, could you do that?
Oh, 100%. Yeah. And what I see like mostly in the ecosystem is a lot of people just like have limiting beliefs, right? And so it's like, that's almost the biggest blocker I come across today. It's not like, and yeah, the models aren't perfect, but like the models need some guidance and whatnot. But like realistically, like the model can also work itself out of almost any problem with a bit of guidance, and you just like asking it the right questions of like, hey, how should we think about this? What are all the ways we can think about this? And you add more logging to the application so you can really see the problem. And these are some things they like need guidance on. But if you just think about it from like a metacognition standpoint of like, how can I just get this LM to think about the problem right and to be able to see all the data it needs to see to solve the problem? And if you don't know what data that is, just ask, like, what would be helpful here for you to understand this better? Because a lot of times they might not look that data up, or they might not have the logging. So just think on like a meta end of like, how do I kind of coach this like semi-intelligent thing, how to get there? And it can. They absolutely can get there. Yeah.
And should people be afraid of all of like, sending private data, like I guess we did talk about this in here, to these type of model services?
Yeah, I mean, I think that depends on what you care about personally. Like, I send my data there. I wouldn't, send any company data there personally.
Yeah.
I don't think I think the history of, data security in just tech in general, forget AI, but like, are these tech companies treating your data well? There's not a good track record.
I mean, like the Cambridge Analytica piece, we all know about that.
It's like Cambridge Analytica is like not even the tip of the iceberg.
Yeah.
Like I worked in ad tech for a while, and like the crap I would see in ad tech was just like unbelievable. And like I worked in like, med tech for like same thing. Like you would, your data is not treated with respect companies don't really care. They'll change the TOS under you and like, you know, make your data fully available. I mean, we saw this like 23andMe, where they're like now selling all your genetic data, right? Like there's no shame in any of these companies as far as like what they're willing to like do with your data. So I wouldn't trust it on that end, right? And I definitely wouldn't send anything like super sensitive, because I just think it's way too dangerous. Yeah.
Unless you're somehow running a model yourself on your own device, I guess.
Which I would encourage people to do. It's really, really fun, right? So there's libraries like Unsloth that you can pick up, and you can just like run, you know, decent models locally. There's Ollama, you know, there's Llama CVP. And you can just run models on your laptop generally. You know, they're not great, but it's fun to be able to like pick them up and experiment, you know, with these models. I really encourage people to do that, because the future is not apps, it's machine learning, and it's dynamic agents, right? When you look 2-3 years out, you know, ahead, like it's not going to be determinism. It's all going to be non-determinism. And like getting yourself familiar with that, I would say now is probably going to be the most beneficial thing.
Well, that is really good advice. And also, it's kind of mind-bending for software engineers to think about dynamic things versus deterministic things. But yeah, I guess that is, if you aren't doing anything else in your software learning for 2026, it's probably good to get your head around it. And yeah, well, thank you so much, Patrick. We are a bit, I mean, I love talking to you, so I'm happy to hang out here, but we should probably wrap up and we can always talk again. But yeah, so thank you everyone who's joined live and asked questions. I really appreciate you being here and engaging live. That is so wonderful that people take the time to ask questions and say hi and share your thoughts. And well, before we just finish properly, I just wanted to also share his QR code for Patrick's LinkedIn. I'm sure he can be friends with people. And feel free to scan that. I'll also put it in the comments here, so you can connect with Patrick on LinkedIn, and maybe he will accept it, or at least you can follow him.
I'll accept it.
He's clearly super lovely. And if you are into wanting to try some models out and working there, said, my name is Erica and I work at Tetrate, and we provide a router for helping you connect to different models from different providers, even allow you to bring your own keys. So if you just want to make it easy for yourself, but yeah, as Patrick said, also try running your own stuff locally. So that would be super cool. But here is the router of Tetrate.ai. You can find that if you sign up. You get $5 free to experiment with, and also recommend you check out Goose. I don't know if people know about Goose, but that allows you to automate some tasks and help you. You can also connect Goose to Ollama locally. So if you're into that, you can use that. That's pretty interesting.
Cool.
But yeah, thank you, Patrick, for joining us. And thank you, everyone who joined. And that's the end for today. And see you next week for those who are around.
Cheers, y'all.
Thank you.